today we shall see how to remove useless symbols from a grammar. When you write a grammar, especially for a programming language, you want to write a compiler, and first step is to write a grammar. You write a grammar, without knowing yourselves you may end up with some useless symbols, because when you write a grammar for a compiler, for a language for that matter, it will not have 3 or 4 rules, it will have hundreds of rules. Then when you write hundreds of rules without knowing yourself, there may be some useless symbols which will not lead you to anything. So, how to find out which symbols are useless and how to get rid of them. So, first let us see what is a useful symbol and what is a useless symbol. If you consider the grammar VTPS, V you can take as a non-terminal alphabet, T as the terminal alphabet, P is the set of productions, S is the set of start symbol. A symbol X is useful if there is a derivation S derives alpha X beta derives W. That is, a symbol X is useful if you can have a derivation of the form S derives alpha X beta derives W, where W is a terminal string. So, from S it should be possible to derive a sentential form. This is called a sentential form. So, from S it should be possible to derive a sentential form which contains X, and ultimately that would also lead you to a terminal string, right. If this is satisfied, then the symbol X is useful. If this condition is not satisfied, then the symbol is useless. Now, if you look carefully at the definition, there are two aspects. One is there should be a terminal portion derivable from X. It should be possible to derive a terminal string from X. This is one condition. The second condition is it should be possible to derive a sentential form containing X from S, or in other words, sometimes it is also put in as X is reachable from S, X is reachable from S. There are two conditions. Are they necessary or sufficient? These two conditions are necessary conditions, but they are not sufficient. They are not sufficient conditions. Why? See, if X is a useful symbol, then from X it should be possible to derive a terminal portion of this W from X. So, it should be possible to derive a terminal string from X, and from S you must be able to reach. But these two conditions, if you use only two of them, it may be, see, suppose I have something like this. I have a sentential form alpha A B beta derivable from S, and this is the only sentential form in which A will occur starting from S, suppose it is that way, and then from A it is possible to derive a terminal string X. Both conditions are satisfied, right. But it may so happen that from B you may not be able to derive a terminal string. If you are not able to derive a terminal string from B, then even though yes, A is reachable and you can derive a terminal string from A is useless. Or instead of putting star, I will write like this. Suppose I have a rule, I have a grammar in which I have a rule S goes to A, B, B, C. Then A goes to A, C. Then some other rules, S goes to C, D, C, D, some other rules are there. Now, is the symbol A useful or not? It is possible to get a sentential form containing A from S. It is also possible to derive a terminal string from A, but if you use this rule and then replace A by AC, still B will be there. There is no rule with B on the left hand side. It is not possible to derive a terminal string from B. So, if a symbol is useful, then it should be possible to derive a terminal string from X, and it should also be possible to derive a sentential form containing X from S. But these two conditions in put together will not imply that the symbol is useful. So, they are necessary conditions, but they are not sufficient conditions. Okay. So, with this idea, let us see how to remove the useless non-terminals, especially most of the times terminal symbols you will not so much bother about usefulness or not, they will be there altogether. But there may be non-terminals which are really useless and you may want to get rid of them. And any time you write a grammar, it is better to write a precise grammar, in the sense that you try to minimize the number of protection rules, try to minimize the number of non-terminals and so on. But at the same time, for example, you may have an ambiguous grammar if you use only one non-terminal, but if you use two non-terminals, it may become unambiguous. So, for some other reason, you may want to increase the number of non-terminals or protection rules by a small factor. So, there will be a trade off between certain things, but generally we do not want to have any useless symbols. So, first let us see one lemma. Given a context free grammar G, V, T, P, S, P is the set of non-terminals, C is the set of terminals, P is the set of protection rules, S is the start symbol. With LG not equal to 5, we will assume that the language generated is not empty. This is without loss of generality, we can assume that. We can effectively find an equivalent context free grammar G dash equal to V dash T P dash S, such that for every A in V dash there is some W in T star for which A derives W. That is, given a grammar, the first step we take is like this. Given a grammar G is equal to V T P S, you construct a grammar G dash equal to V dash T P dash S, such that for this grammar, the language generated for both are the same, it is an equivalent grammar, but in this grammar any non-terminal A belonging to V dash will have the property that it should be possible to derive a terminal string W from A. That is, what you are in essence trying to do is, in this grammar, if there are non-terminals from which terminal strings are not derivable, then you remove them. You remove the non-terminals from which terminal strings are not derivable. In this case, the terminals are not really affected. So, we use the same T, but V dash will be a subset of V and P dash will be a subset of P. You just remove some non-terminals and productions involving them, so that the resultant grammar you have the property that every non-terminal derives a terminal string. The steps are very simple. You use this algorithm to find the set of non-terminals. So, initially you look at rules of the form A going to A B like that, A going to a terminal string. Try to form B dash like this. Look at the productions in P and look at symbols where the right hand side is a terminal one, put those non-terminals here. Then look at those rules where the right hand side will consist of terminal symbols and symbols already present there. That means from each one of them it is possible to derive a terminal string. So, from this non-terminal it will be possible to derive a terminal string. So, include that here. Then again look at these symbols, see the right hand side is made up of terminals and these symbols, and then if the left hand side is different from what is already there, include that. Keep on doing that until no more things can be added. That is what the algorithm says. Old V is empty, then new V is A goes to W for some W in T star, and while old V is not equal to new V, do begin old V is equal to new V will be some more symbols added, old V union A goes to alpha for some A in T union old V star. Then when old V becomes equal to new V dash will consist of that. So, let us take a very simple example and see, it is a very simple idea. So, start with this, I will just write down the rules alone. Start with something like this, A B, S goes to A C, B goes to B, C goes to C. Some grammar is there like this, which has got non-terminals. V has these symbols, V has A, B, C, not A, B, C, S, S, because V has S, A, B, C, E. These are the non-terminals. We will have the following non-terminals. How will you construct? First look at the rules where the right hand side small a, b, c, d are terminal strings, b, c, d they are terminal symbols, non-terminals are capital A, B, C, S, E. The language generated is non-empty because S goes to B, C, from B you can derive B, from C you can derive C, E, D and then E, C, D. So, it is at least B C squared D squared you can derive from this. So, it is a non-empty language. Now, let us see how to find the useless non-terminal and remove it. First look at the rules where you have only symbols from the terminals. So, here you are having only B. So, B has to be included here. And here you are having just C D. So, E has to be included here. So, the first step V dash will it is of course, in the algorithm it is put as new V and old V. So, I will put as new V and old V. Initially old V is empty and new V consists of these two symbols. Then by the algorithm old V becomes new V. So, B and new V is what you already have, and what symbols you are going to add? If the right hand side consists of terminals and B and E. If the right hand side consists of terminal symbols and B or E, then you will include the left hand side. So, here look at this has terminals and E alone, E is on the left hand side, but E is already there. Here look at the rules C, E, D, E is already there, C and D are terminal symbols. So, include C here. So, the next step C will be included. And next stage old V becomes equal to new V, and new V, try to find out whether there is a right hand side which involves terminals and BEC. Look at this one, this has B and C on the right hand side. So, S is on the left hand side. So, S will be added here. Now, after adding S, again next iteration S, old V will have S and new V will have this, and just find out whether any more symbols can be added. You cannot add any more symbol now, because from A it is not, A is not on the left hand side. So, it is not possible to have A. A is not on the left hand side. So, it is not possible to derive any symbol from A. Even if you have something like this, A goes to say some AA, it is not leading to a terminal string, right. So, A will not be included. So, at this stage old V becomes equal to new V. So, these are the symbols. So, the new grammar, you remove the non-terminal which does not lead to a terminal string. Here A does not lead to a terminal string. So, remove A, remove A and the rules involving A on the left or on the right. So, remove this rule, remove this rule, remove this rule. Remove all the rules involving A is a symbol from which you cannot derive a terminal string. So, you have to remove that symbol and all the rules involving A. So, V dash is this is V dash. It is a subset of V. V has all these symbols, but A is useless. So, you remove A, V dash consists of the rest of the symbols, and originally P had so many rules, you remove those rules involving A. Okay. So, like this from a grammar G, see you must note that the language generated is not affected by this. Okay. You are only removing a symbol which is not leading to a terminal thing. So, the language generated is not affected. LG is equivalent to LG dash. So, from a grammar G, you are removing symbols which do not lead to terminal symbols and get a grammar G dash. Here you must note that V dash is a subset of V, P dash is a subset of P. So, we have taken care about the first condition. Let us see about the second condition. It should be possible to derive a sentential form containing the symbol from the start symbol, otherwise it is a useless symbol. So, the second portion is like this. Given a context free grammar G is equal to VTPS, we can effectively find an equivalent context free grammar G dash equal to V dash T dash P dash S, such that for each x in V dash union T dash, there exists alpha and beta in B dash union T dash star, for which from S it is possible to derive alpha x beta. So, we are looking into the second condition now. Given a context free grammar VTPS, we are trying to find a grammar from where from S it is possible to derive every symbol. So, let us see how to do that. Now, you note that we have T dash may be a subset of T. First, let me explain with an example. Consider this example, S goes to AB, A goes to AAB. Grammar something like this. Here what are the non-terminals? The non-terminals here are S, A, B, C. The terminal symbols are A, B, C, D. Now, from this we want to construct another grammar G dash, where the non-terminals will be a subset of P, terminals will be a subset, P dash will be a subset of P, such that from S it should be possible to get a sentential form in which each one of them occur. Now, start with V dash and T dash like this, V dash and T dash. First put S in this, first put S in this, then look at the rules with S on the left hand side, and look at the terminal symbols and non-terminal symbols occurring on the right. Here S goes to AB. So, this AB are non-terminals, you include them. Usually we denote capital letters for non-terminals and small letters for terminals. So, AB are included in B dash. Then look at the rules with A on the left hand side and B on the left hand side. Look at the right hand side. On the right hand side again you are getting A and B capital letters. So, non-terminals are A and B, which are already there, but terminal symbols A and B are occurring here. So, you will be adding A and B. Now, look at the left hand side again, there are no more symbols, non-terminal symbols added. So, no more rules you need to consider. You find that C is not reachable from S. From S, it is not possible to get a sentential form containing C. So, the rule is useless unless you from the start symbol you are able to reach that non-terminal. That non-terminal is not going to contribute to anything. Okay. The language generated consists of strings derivable, terminal strings derivable from the start symbol. So, here from the start symbol it is not possible to reach C. So, C is not going to contribute anything to the language generated by the grammar, and it involves rules, small symbols C and D, terminal symbols, they are also not going to be in the language generated. Okay. So, C and D are useless, C is a useless non-terminal. The terminal symbols C, small c and small d, they are useless, and the capital C, which is a non-terminal, is useless. So, V dash will consist of only S, A, B, and terminal symbols are only A and B, and these productions are involving C and C, D are removed. The useless symbols are removed and the productions involving them either on the left or on the right are removed. So, V dash is a subset of V, T dash is a subset of T, and P dash is a subset of P. Okay. You are not adding any non-terminal at any stage, please remember that you are only removing some of them. So, the next thing is every non-empty context free language you can generate by a context free grammar with no useless symbol. So, you can see that both conditions should be satisfied. That is, from every non-terminal it should be possible to derive a terminal string, and every symbol should occur in a sentential form starting from the start symbol. How do you do that? We consider two lemmas actually. So, start with the context free grammar G is equal to Pt Ps. Then consider the first lemma. Apply lemma 1, that is you make sure that from every non-terminal it is possible to derive a terminal string. Then you get a grammar B dash T P dash S. These two grammars are equivalent, but from this grammar, from every non-terminal it is possible to derive a terminal string. Then from this apply lemma 2, you get something like V2 dash T2 dash P2 dash S. But from this grammar, every symbol in V2 dash or T2 dash is reachable from S. Starting from S, it should be possible to get a sentential form containing every symbol in V2 dash and T2 dash. You must remember that V dash is a subset of V, V2 dash is a subset of V dash. So, obviously by transitivity V2 dash will be a subset of V, and here T and T are equal, here T dash is a subset of T, T2 dash, and P2 dash is a subset of P dash, and P dash itself is a subset of P. This you must. So, what you are doing is starting with the grammar VTPS, first you are applying lemma 1 to see that every non-terminal derives a terminal string. Then you are applying lemma 2 to show that every symbol is reachable from S. Okay. Now you claim that this G2 dash has no useless symbols. G2 dash has no useless symbols. We will prove reductio ad absurdum type proof. Suppose G2 dash has a useless symbol S. Suppose it has a useless symbol X. Then the G2 dash is obtained from G dash by applying lemma 2. So, every symbol here is reachable from S. So, G2 dash has that property. So, S from S it should be possible to get something like this, right. From S it should be possible to get X, then only that is how you have obtained the G2 dash. Okay. Now, every symbol here either non-terminal or terminal, especially non-terminals, whatever non-terminals are occurring in alpha or beta, they are in V dash. Because V2 dash is a subset of V dash, all symbols in V2 dash are in V dash also. Okay. So, here the symbols occurring will be from V2 dash and T2 dash only, right. So, whatever non-terminal is appearing here, that will be in V dash, and in G dash what is the property? Every non-terminal derives a terminal string. Okay. So, it should be possible to derive a terminal string from every one of this. Okay. So, and P2 dash is a subset of P dash, V2 dash is a subset of V dash is a subset of P, and so on. So, from every symbol here it should be possible to derive a terminal string. So, you are able to get a derivation like this, which means that X is useful and it is not useless as you assumed. So, therefore, X is useful, X is useful. So, this assumption is not correct. So, G2 dash does not have useless symbols. So, from a context free grammar you may be able to remove the useless productions and the useless non-terminals. Okay. So, at present it may not be very, I mean you may think why it is, why you should do it and all that. We will convert something to Greibach normal form and Chomsky normal form, and when we do that, the number of productions increase, number of new non-terminals will be introduced, but then ultimately you will find that some are useless. You can remove some of them. Now, here note that starting from V, we have applied lemma 1 to get G prime, and we have applied lemma 2 to get G2 dash. These lemmas should be applied in that order only. You cannot apply lemma 2 first and then lemma 1 next. You cannot change the order. What happens if you change the order? You may not be able to remove all the useless productions. For example, consider this grammar: S goes to AB, S goes to A goes to A. A grammar which has got 3 non-terminals, S goes to capital A and capital B. They are non-terminals, 3 non-terminals are S, A and B, only one terminal small a. What is the language generated by this grammar? The language generated is only one string A. That is only LG consists of only one string A. Okay, so it is enough if you have this rule alone. It is not necessary to have the other two. So, let us see what happens when you apply lemma 1 first and lemma 2 next, and lemma 2 first and lemma 1. What happens? First apply lemma 2, that is from S include symbols which are reachable from S. AB is reachable, so you will keep this, A is reachable, A is reachable, so you will not remove anything. If you apply lemma 2 first, everything is reachable from S, so you will not remove anything, right. Then apply lemma 1, which are the symbols which lead you to terminal strings. S and A lead you to terminal strings. So, this will be removed. So, you will end up with S and A. If you apply lemma 2 first and lemma 1 first, second, if you apply lemma 2 first and then lemma 1 next, that is this condition first and this condition, you will end up with a grammar having 2 rules, S goes to A goes to A, but A goes to A is useless, is not it? Capital A is also useless, but that will not come out. What will happen if you apply lemma 1 first and then lemma 2? If you apply lemma 1 first, from every symbol it should be possible to derive a terminal string. You can see that from S and A you can derive, from B you cannot derive. So, this rule and B has to be removed, this rule has to be removed, B has to be removed. So, at the end you get S goes to A goes to A after applying lemma 1. Then you apply lemma 2, that is every sentential form, every symbol should occur in a sentential form reachable from S. You see that capital A you cannot reach from S now, you cannot reach capital A from S. So, this has to be removed. So, you end up with just S goes to A, only one rule. So, applying these two rules in this order is, these two lemmas in this order helps, the other way around it does not help sometimes, sometimes it may work out and say. Okay. So, now we have seen how to remove a useless symbol from a context free grammar. Next is removal of epsilon productions and unit productions. We want to remove epsilon production. A rule of the form A goes to epsilon is called an epsilon production, is called an epsilon production. A rule of the form, a non-terminal going into another non-terminal is called a unit production. You would like to avoid such productions. A goes to epsilon, A goes to B, you would like to. Why should you avoid such productions? First of all, that length increasing property, length of the left hand side is less than or equal to length of the right hand side, it is violated by rules, this form. Okay. So, in proofs, when this property is violated, the proof becomes lengthy and so on in many cases. So, if you avoid such rules, the proof you can give very easily. That is one idea. The second thing is, why do you want to avoid unit productions? A goes to B, non-terminals. In fact, in some of the examples, like when you wanted to find A power n, B power n, C power m, union A power n, B power m, C power m. The rules we wrote was S goes to S1, S goes to S2, and from S1 you derive this, from S2 you derive this, and so on, is not it? So, such unit productions were easy to write, but why would you avoid them? Why do not you? Why should you not? The reason for this avoiding unit productions is like this. In the compiler, every time when the parsing takes place, the reduction either bottom up or top down, it is taking place. So, when you find that when you reduce using a rule, a semantic routine will be called and a code will be generated. So, if these unit production really do not do anything, like you had E is equal to E plus E, like that. So, these unit production really do not contribute to any proper code, but unnecessarily you will be using them, and each time you will be calling a semantic routine and so on. So, if you use too many of that unit productions, A goes to B, the compile time will be more, compiling of a program will be more. But in order to avoid that, we will see how to avoid the unit productions and how to avoid the epsilon productions. When you avoid the unit productions, the number of rules may increase, but then the number of rules increases very much, then also it is a disadvantage. At each stage you may have to check which rule is applicable for reduction and so on. If there are too many choices and so on, then that time will be more. So, the idea is to reduce the compile time by removing the unit production. If the number of rules increases too much, it depends on the example, particular example. If it is somewhat reasonable, then you will avoid unit production. If it is not reasonable, then it may rather be advantageous to use the unit production. But anyway, unit productions can be avoided, epsilon productions can be avoided and so on. But one thing you must remember, if you avoid epsilon productions, the language will not have epsilon. The language generated will not have epsilon. If you want to have epsilon, you must have at least one rule, S goes to epsilon. If the language consists of epsilon, you must at least have one rule having S on the left hand side, epsilon on the right hand side, and you must also make sure that S does not occur on the right hand side of any projection in order to add that. So, at this stage we will assume that LG does not contain epsilon. You have LG, you have a language which does not contain epsilon. If it contains epsilon, we have to do some modification, as I told you. Now, LG, so L is a CFL and L does not contain epsilon, then you can see that L can be generated. If L is equal to LG for some CFGG, then L minus epsilon is LG dash, that is all strings in L except epsilon can be generated by a grammar G dash with no useless symbols or epsilon productions. So, you have to remove the LG, we can without loss of generality we assume that L does not contain epsilon, and we have to show that L is equal to LG dash and G dash does not have epsilon productions. Now, how do we go about doing this? G is equal to say NTPS, then G dash is same NT, but rules will change. How do we construct G dash? First, find out the nullable non-terminals. First, find out the nullable non-terminals. What is a nullable non-terminal? A non-terminal A is nullable, is said to be nullable if it is possible to derive epsilon from that non-terminal. There is a difference between considering this rule and that. For example, from A you may not have a rule like this, but you may have something like A goes to BC, and then from B goes to epsilon you may have, C goes to epsilon you may have. You may not have A goes to epsilon. In that case B is nullable, C is nullable. A, even though on the right hand side you do not have epsilon, A is also nullable because we are able to derive epsilon from A. We are able to derive the empty string from A. So, in this case A, B, C are all nullable. How can you find out the nullable non-terminals? First, look at the non-terminals like this, which are of this form. Again, you include you put nullable like this. Initially it will be empty. Then look at the rules where on the right hand side you have epsilon, include the non-terminals. After doing that, look at the rules where on the right hand side you have symbols consisting of the symbols already occurring here. Then from each one of them you can derive epsilon. So, you will include that, include the left hand side. Then again repeat the process until no more symbols can be added. For example, you may have something like this. You may have a grammar having number of rules. In that I have A goes to BD, D goes to BC, C goes to epsilon, B goes to epsilon. I may be having like this. So, nullable non-terminals when you find, you have right hand side epsilon for B and C. So, first you will include B and C. Then look at the right hand side which is having only B and C, this B and C is occurring. So, from D you can derive BC, and from B and C again you can derive epsilon. So, from D you can derive epsilon. So, you will be adding D to this. Now, again look at this rule, you are having BD on the right hand side, B and D are already occurring here. So, from B and D it is possible to derive epsilon. So, from A also it is possible to derive epsilon. So, you have A. Keep on doing this until no more symbols are added. The procedure will ultimately stop anyway. So, first find out all the nullable non-terminals. Then what do you do? G dash has the same non-terminals, same terminals, only the production rules change, right. So, how do you change the production rules? If A goes to, for each rule you consider like this. You take one by one the rules in P. For one rule you may have several rules in P dash. The number of rules in P dash will increase. So, take a rule like this in P. For this, what sort of rules you will add in P dash? If this is a rule in P, A goes to C1, C2, Cm will be in P dash. This is not a single rule, it will represent a set of rules. What is that? What is the set of rules? Where Ci is equal to Bi if Bi is not nullable, that is if it is a terminal symbol or a non-terminal which is not nullable, you keep it as it is. But if it is nullable, if Bi is nullable. If it is a nullable non-terminal, you have two choices, either you keep it or you remove it, both possibilities you have to consider. But not all Ci's can be epsilon. You cannot make all the Ci's epsilon, then that means right hand side is epsilon, is not it? So, that possibility you should not consider. So, what you do is, first you find out the nullable non-terminals, then for the rules each one you take from P, and if the rule is of this form, if it is a non-terminal which is not nullable, you keep it, if it is a terminal you keep it. But if it is a nullable non-terminal, you have two possibilities, either you can keep it or you can remove it. Take for example, this simple grammar. This generates epsilon also, this is a Dijkstra generator, generates the Dijkstra well formed strings of parenthesis, taking A as the left parenthesis, B as the right parenthesis, it generates epsilon also. Now, the language without epsilon I want to generate avoiding epsilon rules. So, for this is avoided. For this rule, S is an allowable non-terminal. So, for this rule, how many rules you will have? You will have each S can be present or not present. So, you will have S goes to SA, SBS, all are present. Then 2 of them can be present, 1 need not be present. Two of them may be absent. And all of them may be absent. So, in this one you can replace S by S or epsilon. So, if I replace if S by S, if I keep all the 3 S's, I get this. If I replace this S by epsilon, I get this. If I replace this by S by epsilon, I get this. If I replace this S by epsilon, I get this. If I replace 2 of them by epsilon, I get that, and so on. So, this one rule is replaced by so many rules, and this rule is avoided. Now, the resultant grammar, this does not have epsilon on the right hand side, it does not have epsilon production, but you must feel convinced that this generates the same language. Okay. How do you know that this generates the same language? You can give a step by step proof by induction on the number of steps of derivation and so on. Formal proof can be given. Even in the other 2 lemmas, I have explained with the examples the concept, and the concept was very clear, it was not very difficult. In this case slightly more difficult. You can use a formal proof using induction, I will not go into that. But you must understand that if you are applying a rule, S goes to SA, SB, S at some stage in the derivation tree, and afterwards you are replacing this by S, epsilon and so on, and this by epsilon say. The result you can have by applying, instead of doing this, you could have applied A, B, S, right, you could have applied this rule. So, all possibilities after the once you apply this rule, in the next rule you may use epsilon in these 3 stages, or you may not use at all. If you do not use at all, you use this rule, again you will get the same thing. But the next stage, suppose you use epsilon in 1 or 2 places, instead of doing it in 2 steps like that, you could have used one of these rules. So, the effect is the same. The language generated is the same, you are not changing this. So, given a context free grammar, you can remove the epsilon productions. I shall consider the removal of unit production in the next class, and you can remove the useless symbols. But you must note that first you must remove, the order in which you do is like this. First you remove the epsilon productions, then you remove the unit production, because the removal of epsilon productions may introduce unit productions. So, remove the epsilon production first, then the remove the unit productions, then apply lemma 1, then apply lemma 2. That is, lemma 1 is every non-terminal should derive a terminal string, lemma 2 is every symbol is reachable from S. This is the order in which you have to do. So, we will consider the removal of unit productions like this. Okay. But if you want to include epsilon in the language, what you have to do is like this. If epsilon belongs to L of G, then add the rule S goes to epsilon and make sure is does not occur on the right hand side of this is the way. So, unit production, removal of unit productions and some normal forms like Chomsky normal form, Greibach normal form we shall consider in the next class.